Hey class, Miss Anderson here. This video is going to be on inverse functions. All right, hopefully by the end of this we can find inverse functions and verify that they are inverse functions. The first thing we're going to talk about is the composition of two functions. So composition of two functions is notated like this, which reads like f composed of g of x. So f is our original function, and we are going to apply g of x to the result of f of x. So if our original function f of x is equal to 2x and g of x is equal to 5x minus 1, I can plug g into f like this. So you look at the outside function, and that's the one you start with. So f is on the outside, so start with f of x equals 2x. Then you'll notice instead of f of x, we now have f of g of x. So in the place of the x spot on both sides here, we're going to put in the g of x function, which was 5x minus 1. So we had f of x is now f of 5x minus 1, and then 2x is going to be 2 times 5x minus 1. So this is in function notation, which shows our input of our function, and now our input is another function, so we've changed that input. Now we're going to resolve it. So this is giving me f of g of x, which is kind of confusing, and sometimes we just label that a new function. Maybe we just use a new letter, h of x, or you could just do y equals. So all of those would be equivalent. The left side here is just showing me that's the output of my function. And then here I would distribute the 2, and you would get 10x minus 1. So you could relabel that as h of x, or just use y equals. So this is our composition function. So h of x is our output. For example, if you wanted to find like h of 3, or then you would plug in 3 for x, and you would get 30 minus 1. So you'd have like the ordered point 329. So input, output. So that's our composition of our function. Okay, let's try it the other way around. So this time we're composing g as our starting function, and we're plugging f of x into g. So we start with g, so I always like to write down my original function, 5x minus 1, and then I'm replacing the x with my function of f of x, which was 2x. So then this is going to give me g of f of x, and maybe I want to call that h of x again, or e of x, or something different. And then this time it's very similar, but the minus 1 on the end is not in the parentheses, so when I distribute the 5, it just goes to the 2x. So 5 times 2x is 10x, and we have minus 1. So 10x minus 1. So they are similar. Whoops. And I guess I caught my mistake on the other side. I didn't distribute correctly, because it should have been 10x minus 2. 10x minus 2 on that one. So they're similar but different, because the first one I was supposed to distribute the 2 to both, and then the second one I only distribute to the first parenthesis. All right, then it asked me to list any domain restrictions that go along with these. And since I started with linear functions, which means it's just x to the first power, and I ended with linear functions, and my restrictions are there any possible possible restrictions to what you can plug in. Input restrictions is essentially another way to think about domain restrictions. And this is just 10 times x minus 2, and so there's no restriction to what you can multiply by 10. So no restrictions. And the other side would be the same idea. Okay, so that was composition with linear functions. Let's try composition with exponential, or our rational functions that we've been working with. So here are two functions. We have 2x to the 1/3, and g of x is x to the 3/4. First, I want f composed of g of x. So f is our outside function, so we're going to start with f of x, and f of x is equal to 2x to the 1/3. Then we're going to replace our input, so our x, with our g of x spot. So where we had our x before is going to be our g of x function now. So now I have f of g of x is equal to, and then you're going to follow the order of operations, so work through this carefully. Exponents comes first, so you're going to do this piece first, and you have a power raised to a power, and the exponent rule then is to multiply the exponents. And when you are multiplying with fractions, you're going to take the numerator times the numerator, so like 3 times 1, and then 4 times 3. So you're going to get 2 on the outside here, and then x to the 3/12. Then 2 times x to the 3/12 will be 2x and 3/12, so you can simplify to 1/4. And that's going to be our new function. We can call it h of x, leave it as f of g of x, put y equals, but that's our composition function. Now we need to find domain restrictions. I think restrictions are easier to work with in radical notation. So if I thought about this and rewriting it, 2 is on the outside. This would be 2/4 roots of x to the first. And that helps me think about domain restrictions because we can't, in the real number system, we can't take even roots of negative numbers because that either gives us imaginary solutions or no real solutions. So we want to have all positives under here, which means that since I have a single x, my restriction would be x greater than or equal to 0. Be my domain restriction for that. Okay, this time I want f composed of f. So f is my outside function, so we're going to start with f of x, and that's equal to 2x to the 1/3. Then we're going to replace my input x with an x again. So we're going to be plugging in 2x to the 1/3 into 2x to the 1/3. You're plugging x into f of x into f of x. All right, then carefully follow your order of operations again. This is going to give me f of x. And exponents come first, and we have a product, which means this is 2 times x to the 1/3 to the 1/3. When you have a product to a power, you apply that exponent to both, and when you're doing a power to a power, you multiply their exponents. So 2 has its own exponent. It's an implied exponent of 1 there. So we're going to do 2, and then 1 to the 1/3. It's going to be 2 to the 1/3. X to the 1/3 to the 1/3. It's going to be x to the 1/9. So multiplying exponents there. Then I'm multiplying here, so I end up with a 2 times a 2 to the 1/3. These have the same base, and so I can apply my exponent rules. And the same base, you add exponents. So remember again, that's 2 to the first power times 2 to the 1/3 power. So we're going to be adding 1 plus 1/3. And 1 plus 1/3, you want a common denominator, it'd be 3/3 plus 1/3 is going to be 2 to the 4/3, then x to the 1/9. So you can leave your answer like that, or you can change it back to radical notation. If you're going to change it back to radical notation, you would want these to have the same root, and so you'd want to change 4/3 into ninths. So 4/3 would be the same thing. If you multiply this bottom by 3, you get 9, and then top by 3, you get 12/9. So 2 to the 12/9, x to the 1/9. Then you'd be able to put it all under the 9th root of 2 to the 12, x to the first. And then since we have 12 2's, we could take 1 2 out. And then we'd have 9, 10, 11, 12, 3 left over. So 2 cubed, which would be 8x. So that would be simplified radical notation. Then for restrictions, since we have an odd root, there are no restrictions. We can take the, you can plug anything into a cubed root, a 5th root, a 9th root. There are no restrictions for an odd root. Okay, the next thing we're going to talk about is inverse functions. So for an inverse function, if a function plugs in x, you get out y. The inverse takes in y and puts out x. And so here I have a relationship between these numbers. I've plotted these points in black here: 0, 1, 2, 3, 4, 5, 6, 7. Now I'm going to do the inverse. So if my first point was 0, 1, the first point on my inverse would be 1, 0. I'm going to graph that. It's right there. Then my next point was 2, 3. My inverse would be 3, 2. I'm graphing that. And then I have this dashed line, so as I graph it, you can see that my points are being just reflected over. So like if I took this point that's graphed right here and I reflected it over, my reflection should be right there. They're being reflected over this diagonal here that's actually the line y equals x. So my next point that I just graphed there was the inverse of the 0.45, so it was the 0.54, and you can see that matches up. And then my last point would be 7, 6, the inverse of 6, 7. And then you can see how it is reflected over that line y equals x as well. So an inverse of a function reflects it over the line y equals x, which is the parent function of the line. It's just this positive sloping line, goes through the origin, cuts the Cartesian plane in half here. So that line is our reflection line for inverse functions. I think the easiest way to graph an inverse given an original graph is just to find some points of the original. So like this point on top here would be -1, 0. So then the inverse would be 0, -1. Graph that. Then another point, the original, like this one, is 0, 1. So then the inverse would be at 1, 0. And then maybe one more. This point is 3, 2. So then the inverse would be at 2, 3. And so the inverse function here ends up looking like that. Now, if it's kind of hard to imagine, but if you had the diagonal right here, you can see how these would flip. This point reflects up here, this point reflects here, and this point reflects here, which is why we end up getting that looking shape there. So the inverse is the same shape, but it looks a little different there. So that's how we would graph an inverse. Find points from the original, then swap out the x and y. The inverse for this one ends up looking like this. I'm just going to put those points on there, and you can pause it and write that down if you'd like. Just to save some time, I'm going to move on though, since I did that full one. Inverse functions, formally defined to be when you can reverse into another function. If any function f takes x to y, then the inverse f to the -1 will take y to x. So this is the notation we use to represent an inverse function. This is not actually a -1 exponent. It's just the notation in this case that we're using to denote the difference between the original and its inverse function. So for example, our function will take, if x goes to y, then y will go to x in the inverse. So if this is our original function, f of x equals -3x plus 6, that's the same thing as y equals -3x plus 6. The inverse will switch the x and y. So that's the first thing you're going to do to find the inverse. So you're going to have x and y are going to be swapped. So instead of y equals -3x plus 6, it's going to be x equals -3y plus 6. Then you just need to resolve for y because you want to find f of -1, which is the same thing as y equals still, but the inverse. So resolving this for y, you want to undo your addition of 6 by subtracting 6 to both sides. And then those are not like terms, so we just get x minus 6 equals -3y. Then to get y by itself, undo the multiplication by using division. And so we got y, which is actually y inverse, would be x minus 6 over -3. So you can leave it in that format, or you can separate it out, which I think personally looks better. I'm going to use the inverse notation, f inverse. This is a 1x over -3, and 1 over -3 is -1/3 x. And then we have -6 over -3, which is +2. So this is a linear equation, in which case this would be written in slope-intercept form. So especially if you want to graph this, it'd be nice to write it like this so you can get your slope and your y-intercept. You can graph it easily. So, or you can leave it like this if you don't want to split it up. But you're just dividing that 1/3 into both and simplifying. Okay, In this case, our original function was linear, our inverse is linear. You'll notice that our slope was the reciprocal of the original because we reflected over that line y equals x, which makes our slope the reciprocal, and then we start at different y-intercept points. But first we started with a linear function, so our inverse is still linear. We'd have no restrictions on either of those functions. Our next example is an inverse of a quartic function or a power function, power of 4. So you might think to yourself, the inverse of an exponent is a radical. So these are going to be inverses of each other. And so we're going to find that inverse by first starting with y equals x to the 4th plus 3. The inverse swaps around those x's and y's, so switch those. So y equals instead will be x equals y to the 4th plus 3. Then resolve for this y value here. So isolate the y to the 4th by subtracting 3 on both sides. I'm going to get x minus 3 equals y to the 4th. Then use the inverse. So the inverse of the exponent is using that radical. It's an exponent of 4, so we're going to need a 4th root to undo that. That's going to go over that whole thing. So this 4th root, we'll get rid of that. And we will have y equals the 4th root of x minus 3. And then we're going to add this little notation piece, which is looks like a -1 exponent, but it is the notation for the inverse. So that just means y inverse equals the 4th root of x minus 3, or you can use function notation. So f inverse of x equals the 4th root of x minus 3. And then this notates our input. So when we're looking for restrictions, we're looking at what would cause us problems or possible input restrictions on this side. Since we have an even numbered root, you can't have negative values under here because you can't take the square root or the 4th root of negative values and get real solutions. So we're looking for what in here. That means this x minus 3 has to stay greater than or equal to 0. So if you're looking for just what x has to be bigger than, that means that your x's would have to be greater than or equal to 3. So those would be your restrictions for this piece. Notice in our original function we had an x to the 4th power. Now there are no restrictions for what you are when you are plugging in stuff with exponents. X to the 4th power is fine. You can take -2 to the 4th and get 16. That works. But you can't take the 4th root of -16 and get an answer. So the original in this case had no restrictions. The inverse did. So we have to be careful, especially with exponent ones. And then we're going to verify that they are inverses. So that's the last thing we do in this unit is verify. So these are the two functions that I found earlier. We found y equals -3x plus 6, and then its inverse was -1/3 x plus 2. That was our first example for finding inverses. Now I'm going to prove to you that they are inverses. We do that by using composition. If you take the function and you input its inverse and you simplify it, it should equal x. Then you have to do it, and you do it the reverse way. So you take the inverse and you put in the original, and when you simplify it equals x. And if you get x for both, then they are inverses of each other. So let's try this side first. So this one I'm starting with the original function on the outside. So f of x equals -3x plus 6. And I'm going to replace the input of x with my inverse function, which was -1/3 x plus 2. So that's going to go in here for where my x was in my original. And then I'm going to use the distributive property here. So -3 times -1/3 is going to be 1x. -3 times 2 is -6. And then I have a plus 6. -6 plus 6 is 0. So it does in fact simplify to x. Now I just have to verify doing it the other way. I should also get x. This one I'm starting with the inverse function on the outside, and I'm plugging in the f. So the inverse originally was -1/3 x plus 2. Now I'm going to replace my input with my original function. So I wrote out the parentheses. Now I'm going to be plugging in f of x, which is the -3x plus 6. So the -3x plus 6 in the x spot. Then applying the distributive property again, negative 1/3 times negative 3 is 1x, negative 1/3 times 6 is negative 2 plus 2, and these simplify to 0. So it does in fact simplify down to just x. They both equal to x, so then we could say, therefore, they are inverses. So we are able to find the inverse, verify inverses by using composition, and then that. I'm going to save the last one because this is actually in your homework, so I want you to give it a try. In a previous video, I do have this example explained and walked through. It's also written out in the completed notes and in the answer key of the homework. So if you want to see it done, you have a few options there. But for the sake of this video, I'm going to stop. Thanks for watching.